This is the first lesson for Chapter 10, Reactions and Equations. And what we're going to look at today is how a chemical reaction can be represented using symbols and words. So our learning targets today is that we're going to review how to recognize evidence of chemical change. And you should be able to use the symbols plus, arrow, and physical state abbreviations to write word and skeleton equations. There are three types of equations that we'll learn how to write. One is a word equation, one is a skeleton equation, and then the third one is a balanced chemical equation, which will be in our next lesson. So chemical equations, and there's a difference between an equation and a reaction. The reaction is what physically happens when you put two chemicals together. The equation is how we describe it on paper. So chemical equations are like recipes for making new compounds. And again, a compound is just two different types of atoms that are bonded together. Chemical reactions are chemicals that have undergone chemical change. So we never write a chemical equation unless some sort of chemical change or reaction has taken place. So to give you an analogy of how chemical equations are like recipes, I have here a really simple recipe for microwave brownies. And if you haven't tried these, they're not too bad. But you can see here the ingredients are listed first. A box of brownie mix, an egg, and 2 single-serve containers of applesauce. I guarantee you can't taste the applesauce once it's mixed in. But you mix the ingredients, divide it into 2 9-inch paper plates, preferably the ones that are pretty sturdy, and then you cook them one at a time in a microwave for 3 to 5 minutes, and then cool them before you cut into 24 brownies. Now, this recipe could have been a lot longer and a lot more complicated, but because it uses some norms or standards, like listing the ingredients first, assuming that you know a little bit about baking if you're using a boxed brownie mix, and some abbreviations, we're able to shorten up the recipe and give you a pretty good idea of what it is you're making. So in this recipe, we have ingredients that are transformed. So we start out with the raw ingredients and end up with a brownie, which undergoes chemical reactions. The quantities that we use form a ratio that can be easily multiplied or divided. So if we wanted to double this recipe, we would have 2 boxes of brownie mix, 2 eggs, and 4 cups of the applesauce. The format is consistent. We see the ingredients first. We also assume that there's a certain amount of knowledge about the recipe that allows us to simplify the directions. And then we have standard symbols that allow for shortcuts that are easily understood by everyone. And so in the directions, for example, when you see MIN, period, you know that means minutes. So the same thing is true for a chemical equation. We only write it if the ingredients are transformed or if there's a reaction. The quantities in a balanced chemical equation form a ratio that we can easily multiply or divide. The format is consistent. We always see the ingredients on the left side of the arrow and the products on the right side. And then we have some standard abbreviations or symbols that allow us some shortcuts. For example, we don't have to write out the word hydrogen. We can just write the symbol H or H2. All right, so again, how do we recognize when we're witnessing a chemical reaction? If you go back to previous units, we talked about this at the beginning of the year, that evidence of a chemical reaction comes in or usually takes 4 different shapes. So for all of these indicators of a chemical reaction or evidence of a chemical reaction, the change is unexpected. So for example, when you put yellow and colorless liquid together, you would expect it to be just a lighter yellow. But because it turns to a completely different color, that unexpected color change is a sign of a chemical reaction. Production of gas or bubbles, or sometimes that gas is in the form of an odor. And again, it's unexpected. If you put a beaker of water or a pan of water on the stove or on a Bunsen burner, it will heat up and the state will change from liquid to gas. That's expected. But if you put 2 room temperature chemicals together and all of a sudden they start bubbling, that's an unexpected production of gas and indicates a chemical reaction. The third one is unexpected production of heat or light. So if you were to take just a stick of wood and rub it against some sandpaper, nothing would happen. You would not get a flame or excessive heat. But because of the chemical reaction that occurs, because of the chemicals on the end of a matchstick, when you apply that friction, it bursts into flame. That's an unexpected production of heat or light. Another example of that would be putting 2 room temperature chemicals together and having them get really hot. Or if you've ever used a chemical ice pack, when you bend the ice pack, it immediately starts to turn cold, and that's the absorption of heat from the surroundings. And then solid or precipitate. And a precipitate is a word that we're going to use a lot in this next unit because many of the chemical reactions that we do produce precipitates. So if you were to take that light blue liquid and put it with a colorless liquid, you would expect it again to turn a slightly lighter blue color. But instead, it forms black particles, and at first it might look cloudy, but eventually they would settle to the bottom. And that's what precipitate means. It means something that settles to the bottom, like rain from the clouds settles to the earth. Now that we know how to recognize a chemical reaction, we can learn how to represent it using a type of equation. And we're going to learn 3 types of equations. The first one is a word equation, then a skeleton equation, and then the third type, balanced chemical equation. When we're writing those equations, we always use the same format, similar to the recipe. We always start with the ingredients or the reactants and end with the products or what we're making. And those two are always separated by an arrow. And so that arrow means makes or reacts to produce or reacts to make or yields whatever it is that we're making. It separates the reactants from the products. The other symbol that we commonly use is the plus sign. And the plus sign means and it's really just a separator, kind of like a comma is a separator. So if we've got more than one reactant, we put a plus sign between them. And if we make more than one product, then we put a plus sign between those. Another symbol that we often use is one for states. Since a transformation takes place, we often end up with an unexpected state, or sometimes the reaction will only occur if the initial reactants are in a particular state. And so we indicate that by using a lowercase letter inside parentheses after the formula for the chemical in the equation. So for example, if we start out with salt, which is NaCl, if that salt needs to be in the solid state as it's shown here, we would write NaCl and then parenthesis, lowercase s, parenthesis, to indicate that it needs to be in its solid form. Another state that we might indicate is liquid. And liquid means that we have a pure substance that is in its liquid state at this particular temperature. So for example, water is a pure substance, and at room temperature, it is a liquid. If, however, we took this salt and dissolved it in the water, then we would have a solution. And the state that we use to indicate that we have a solution is AQ. And that stands for aqueous, or I've heard it pronounced aqueous, and it means dissolved in water. Notice aqua is kind of the root of this word, water. So the salt dissolved in the water is an aqueous solution. And many times a reaction will not occur unless we have first dissolved an ionic compound, for example, in water. Okay, so pure water in its liquid form is L, but once we dissolve a solid in the water to make a solution, then we say it's AQ, aqueous. And then we also have gas, which is lowercase g, and I'm just showing the bubbles here because that's the form that we usually see those gases in. All right, so we're going to start with a word equation. And a word equation uses these symbols that I've just given you, the arrow, the plus sign, and then the S, L, G, and AQ, along with the compound names to describe a reaction. And there is a reaction here in a video. I'm struggling a little bit with internet, so I'm not going to show the video, but basically it's taking iron, which is in the form of steel wool, and reacting it with chlorine gas, which is a yellow gas at room temperature. And they react to form iron 3 chloride. We see evidence of the chemical reaction just in this picture, because as soon as we dip the steel wool into the flask of chlorine gas, it immediately bursts into flames and gives off a tremendous amount of heat. And then we see this cloud of orange forming. And those are solid particles, and after the reaction is over, they eventually settle to the bottom of the flask. And we can see that they're actually solid particles of iron 3 chloride. All right, so if we wanted to take this description and turn it into a word equation, this is what it would look like. So we're starting with iron, and here it was in the form of steel wool, which is a solid, and chlorine, which is a gas at room temperature. And then this is where the magic happens. This is where the reaction occurs. And once it occurs, we no longer have the element iron and the element chlorine. We now have the compound iron 3 chloride, which is a solid. Now this slide is just to show you that when we're describing a chemical reaction, we don't always describe it in order. For example, I could have said that iron 3 chloride is produced when I put iron, metal, and chlorine gas together and they react. That doesn't mean, though, that I change the way that I write the equation. I still want to write the beginning chemicals first, then the arrow, and then my products. And we can see here, solid iron 3 chloride is what is produced, so that goes on the right side of the arrow. All right, this is why it's been so critical to know how to write chemical formulas correctly, because a lot of times the description of a chemical reaction is in the form of a word equation, and then we need to take that word equation and change it into a skeleton equation so that we can balance it. Skeleton equation just uses the bare bones of the reaction and uses this just symbols. And so we take these words or names and we change them into formulas. We use the same placement of the pluses and the state symbols, and notice that the arrow's in the same spot. All we've done here is changed the words or names into formulas. I've also left these little lines in front of each formula because when we start balancing, that just assures us that we have plenty of room to do the balancing. At the moment, you don't have to worry about those lines. So, iron as an element, we look on the periodic table, and the symbol for iron is Fe. Chlorine, when we look on the periodic table for chlorine, we see a little 2 beside it, or it's underlined if you have a different periodic table, which means that it is diatomic. When chlorine gas is by itself as an element, it always exists in pairs because it's so much more stable that way. So when we write chlorine as an element, we have to write it as Cl2. And I'll review diatomics on the next slide. Now notice that the product is iron 3 chloride. And so when we write the formula, we're going to use the information we have in the name. And this tells us that iron has a +3 charge. And if we look up chloride, which is chlorine in its ion version, its charge is -1. And so when we crisscross, we need 3 chlorides to balance 1 iron. And so the formula is FeCl3. Again, we don't worry about chlorine being diatomic in the compound because in the compound, it's forming that crystal based on charge. Here, we just have a neutral element, and it's formed a covalent bond so that it's more stable. All right, so just to review diatomic elements, again, these are elements that exist in pairs, and I call it the rule of 7 because it helps me to remember that there are 7 elements that are always diatomic, and hydrogen is one of them, which is the oddball. Hydrogen's always the oddball. And if we go to element 7 on the periodic table and then make a 7, those are the other elements that are diatomic. Okay, so when we write the symbols for these 7 elements, we're always going to write them with a 2 subscript. On the next slide, I'm going to show you a word equation for a chemical reaction that uses hydrogen as an element and bromine as an element. And we notice that these are both diatomic. So when we write our skeleton equation from this word equation, we need to keep that in mind. So hydrogen, because it's diatomic when it's by itself as an element, and we know it's an element because there's only one name listed there, we have to write it as H2. And then whenever we have the state symbol in the word equation, we need to use it in the skeleton equation as well. We said bromine was diatomic as well, so Br2. And then what's produced here, and eventually we'll learn how to predict what is produced, is hydrogen bromide. Well, there's no prefix on the bromide, which means that this is an ionic compound. So hydrogen, if we go to the top of the group, has a +1 charge. Bromide is Br with a 1- charge. And so since the charges are the same, we only need one of each to write the formula for hydrogen bromide. Okay. All right. Now I'm going to give you just a second to see if you can spot the correct skeleton equation from this word equation for making carbon dioxide. And you can stop the video if you want to take a second to think about it. All right, so I'm going to immediately cross out B. And the reason I'm doing that is because I notice in the word equation that I have symbols for the states. And I'm sorry, I forgot to write the G over here for carbon dioxide. So I'm going to eliminate B because it doesn't list the states. Then I can see carbon monoxide. Carbon with no prefix means one. Mono means one oxygen. So 1 and 1, 1 and 1. So carbon monoxide is written correctly in both of them. And then if I look at carbon dioxide, no prefix in front of carbon means 1, and 2 in front of oxide means 2 oxygens. So both of these formulas for carbon dioxide are okay. The thing that's different between these two are the oxygens. One is listed as O2 and the other one is just listed as O. Since oxygen is one of the diatomic elements, when it's by itself in a chemical reaction, it will always be in the form of O2. So this diatomic element O2 is correct. Therefore, the first option is the correct option. All right, and then eventually what we'll do is learn how to balance these equations, because we can see here that if we start with 1, 2, 3 oxygens and only end up with 2 on this side, we have to figure out where that third oxygen went. So that'll be the balancing that we do next. For the moment, I need you to work on practicing writing word equations and skeleton equations using the formulas. On the agenda for today, there's a word equation that I'd like you to practice, and it will be on your bell ringer tomorrow.